Hello guys, today we're going to cover two many things. How to declare arrays in two ways, and another thing we're going to take the little Endian, which is how we store data in memory. And first I want to give you the arrays, because it will help you better to understand the little Endian. Let's say I have include. Alright, and now we want to declare an array. C and the data. We have two ways. First way, let's name it list, and I can say define word or word. And if it was signed, if you want to do signed, I could say signed word. A good question is, I'm not going to answer it now, I'm going to leave it. Word takes a negative value. If I give it -7, it will take it. So why do we use sign word to represent negative value? Like now, if I say this equals -7, it's good. If I say list word as sign word, declaring it as negative, so this is also possible. The question is, what's the difference between them? If I can put -7 here in word, why do I have sign? I'm going to leave the answer to you guys. I'll answer it next time. Think of it. I think it's hard to find an answer in wrong. Let's say sign word, and let's put 1000. Hexadecimal, those are 1 byte, and those are 1 byte. And I can say, let's put it 64, 70. This is decimal, remember, by default. I can do this, and this is 1 byte. I can say byte. I declared a list or an array of 3 elements. First element, this one. Second element, and third element. I can also declare, let's say, list 1 and say find byte or byte, and print over there. And let's say, let's make it double. The word is 2 bytes, double word is 4 bytes. So let's go into 1, 2, 3, 4 bytes. Let's say this one. And let's go 1, 2, 3, 4, 5, 6. An array of 2 elements. And we also can define array using what's called the DUP operator. The DUP operator takes the size, let's say an array of size 5, initialized all to zeros, or uninitialized, or I can say 10. Let's make it, we didn't give it the size, and let's say 5, so that's 0. And I can say array 1 byte, and I could say 1, 2, 4, dot, an array inside an array. Don't think this is two-dimensional array. Let's do it. And let's say 1. What this is an array of 1, 2, 3, and 1, 1, 1, 1. Those are the 4 ones, and those are the 2. So an array of size 6. Both of those are an array of size 6 element, and we have 6 bytes. This is the big. So we have this small array that problem. So now go code. Let me draw the memory of this one so we can understand it in a better way. Let's look here too. A word to byte. I have 6 bytes. Here I have 8 bytes plus 50. 5 bytes plus 19. 25. So I'm gonna have 25. Oh, and let's make 2 columns. But I'm just gonna show you this. So we're only 1 column. Let's fix this first. And let's say this takes the address. And let's say you're gonna see different things. You can start from here. Let's say address 0x0000, for example. Or we can start from bottom and go up. This will be address 0x0001. And let's assume this is byte addressable memory. Byte addressable memory meaning each byte has an address. Each of those is a byte. If I had a word addressable memory, each word will have an address, meaning every 2 bytes will have 1 address. Byte addressable memory, every byte has an address. Word addressable memory, every 2 bytes have an address. And this will be 0x003. This is 4, 5, 6. This one to show you. We'll have the rest later, but let's see this. Now let's see, we're going to start with address 000. What do I have? Now the little Endian kicks in. The little Endian kicks in when I have more than 1 byte in a byte addressable memory, and more than a word in a word addressable memory. Meaning, how am I going to save this? The 1000 hex. Am I going to say 1, 0, 0, 0, 0? And why is that? That every 2 digits, those 2 digits are a byte, and those 2 digits are a byte. The 0, 0 is a byte, and the 1, 0 is a byte. And this is a byte addressable memory, so every, let's say, here, every place takes a byte. Little Endian. How memory is stored. Little Endian and Big Endian. This is Big Endian. Little Endian, which we're going to cover, and mainly our objective is sorry, Little Endian, and it's with an E, not with an I. The most significant byte, the lowest significant byte, at the lowest address. So this is the way how it's stored. This is the first element. This is, let's give it a color. This is the first element. Little Endian. How do I know least significant byte? The right one has the lowest value. Remember when we did the convergence, we always started from where? We started with 1, 2, 4, 8. So this bit has the lowest value, 2 to the power 0, lowest value, 2 to the power 1, 2 to the power 2, 2 to the power 3. So when we go left, the value increases. So for those 2 bytes, this is the least significant byte. This is the high significant byte. So the least significant byte at the lowest address, which is 0, 0. Now the 70, we convert it to binary. This is going to be saved in binary, but I put it in hexa. 70, if I wanted this in binary, what will it be? It's going to be, let's say we have, so 1, 2, 4, 8, 60, 32, and 64. And each of those, this is a bit, remember, this converting is into binary. Now we took this. So here I have 1, 2, 3, 4, 7 bits. I'm going to have the 64, 7 bits, and let's say 1, 0, 0, and 0, and 1, 1, 0. This is binary. This is binary. So now we have 7 bits, and we have it as this array as words. So 2 bytes, 2 bytes, 2 bytes. I'm going to add word. So then 9, 0, 0. So this 0, 1, 2, 3, 4, 5, 6. Least significant byte at the lowest address. Least significant byte at the lowest address. 0, 1, 1. 64, 1, 2, 3, 0. Let's put those hits up, and you know how to put those in. Back 8, and this is 0, 0, 0. This is another. And this color. This is the second word. Then I have here. Then I have this. So I'm going to put those. This is the byte at the lowest address. Little Endian. So it's going to be 0, 1. And 1, 0. This is the third element of that array. This is the memory of the program. Let's see what we have. Then we have a D word. The D word takes 4 bytes. So it's going to take those 4. And I'm going to say the least significant byte and the lowest address. So it's going to be 78, 56, and this is hexadecimal, guys. You can convert it to 34 and 12. Here I have 1, 1, 2, 2, 3, 3, and I don't know, so that's 4, 4. So I'm going to have 4, 4, 3, 3, and 1, 1. Okay, so this would be this is second let's say here we're going to have a list. List 1. Here we're going to have list 1. This is 11, 12, 13. I don't care about those addresses. We're going to see why in a minute. Now I have an array of 5 bytes. So think of this as an array. 5 bytes, and we declare them all as 0. So we're going to have 5, 0, 0, 0, 0, 0. Then we're going to have 1. That's what array 1. So we took how to do little Endian, how to put the values in memory, and we took how to declare arrays of fields. So I made this, and the other one is DUP operator. We have another. And let's say I want to find the size of this array. Let's say size was $sign is called the current location pointer, and minus list. Let's look at memory. And remember, it's going line by line. So we put this and it's going to size. Current location pointer will be waiting here. It will be waiting here. It filled those, and it filled this, and now it's waiting here. Current location pointer. So it will be at address 6. Address 6 minus list, which is what? 0. Address 0. If you think about address 0 and address 6. So this will give me what? 6 minus 0, and this will be 6, which is the number of bytes in the list. Number of bytes in the list. Find how many elements I have. I divide it by word, which is 2 bytes, divided by 2. This will give me can say size equal $sign minus list, the name of the array or list, divided by the word. If it was a double word, I'll divide by 4. If it was single bytes, I'll divide by 1, which will give me 6 elements. And we can use those for what? For loops. Because arrays we're going to use loops. And here I'm going to say, let's go back to the memory and look at the memory. I have list 1 at address 6. So let's say size 1 equals $sign current location pointer minus list 1. This is going to give me this one at 6, and let's see what's the current location pointer after inputting this. It's going to be address 14. Current location pointer here. Fill the 11 and it's waiting here. So it's going to be 14. And 6. Total of 8 bytes, the size of the array, divided by 4. So the base type of the array gives me 2 elements. We have 2 elements. 2 elements in this array. And this the assembly that comments. This does it. Now what happens if I you wrote this and then I took this and put it here. It's going to be $sign, which is going to be after filling address, which is going to be address 26 minus list, which is going to be address 0. So it's going to give me the whole memory. So be careful. After clearing each array, I calculate the size of it. Here we have 4. So I can say here, this one we don't need to do it, it's 5. Here I can say size 2 equals what? $sign. And I'm not going to do it, we will check here. Minus what? Array 1. And this will give me the size of this array, which is 6 bytes. 6 bytes. Now let's do this main process. And that will exit. Main end process and end main. Now array important. Let's say if I'm gonna add this one. And here is how we're going to use the index. Move. I'm going to say 2. I'm going to use EAX because I have a new word. If I wanted to do list, which is this one, I use AX. If I want to do this one, I will show you AX, and I move list 1. List 1 is the first element. This one. It's actually list 1 plus 0. But we don't care about 0. And then I'll say add to the accumulator, which has list 1, which is the first element, which is this. Add to it. This. Add list 1 plus 1. Plus 1 amount. Okay. That's why going to memory is going to be really important. This is list 1 plus 0 plus 1 plus 2 plus 3 is going to be plus 4. So because it's a new word and we can do it this way or that. And let's see the registers. So we can word, record, and it's here. So it's going to be, and then we go in that group, and it's going to just check the size of this to this for now, just so do this. This one for you. And I just want to see them in the register. So here I say add or move. I'm going to move the first element, which is what? 1. And I prefer clear, but let's see it first. And clear here, EAS, move to AL. Why? Because it's 1 byte. Array is 1 byte. And I say array 1, the first element. Then I say add to AL array 1 plus 1, because it's a byte. So when the word, I say array plus 2, AL array, and we're going to take how to do it in loops. I just want to show you this so you can understand it better. Plus 2 is going to do AL and array 1 plus 3 plus 2. Okay, that's good. Look at here. So show me the registers. That's really important. Now, please now to AX. So, or let's make this, but I want to move it from list 1. So if I say list 1 minus 1 is this, minus 2 is this, minus 3, minus 4, minus 5, minus 6. Let's put list 1 minus 6. See, going reverse order. 6, and then we can do this. Of this website, then for then register. And we're done with this. Let's save it as program 6. Assembly. Let's see what that's. Rules. Three. 6. That is fixed equals close. So now to the favorite. Now graduation. this way to like size to it. So here, that's the problem. Since we need to use the director, let's see this works. I will send us all files. That one simple. So it's just not like size, so that like size 3 this way. Okay. Doing like the side is 0, so we got it okay. Instruction operands must be the same size. Line 8. So what? This one is keyword. Right? Fine. Okay. Good. Just to put a word actually as a double word, so this will work. Good. So that's good. So that. And instruction operands must be the same. So this one and 6 is so this one has okay, and let's go. So this one So, zoom. Now that's a problem for me because another problem. It's, zoom again. So let me tell you the first one. EAX has a value of 1, 2, 3, 4, 5, 6, 7, 8. And that's right. This one, this one. And now we're adding a list of this plus this in hexadecimal. So let's see what the result is. C 4 and 8 is 12. Give me C, B 4 and 7 is 11. And 3 and 6 is 9, 9. C, B, and I'm reading it from right to left. C, B, 9, 8, 6, 5, 3, 2, 3, 2. Up here. then what? Anyway, very graphic, and I'll have a screenshot and I'll add a description. And we can do that screen. So now we're doing, let's say, move array 1, which is this one, 5 to AL, which is 1. And I told you you might have a problem. We need to move AX 0. So we move AX 0. I left it. We don't have a problem. And we got that problem. So full output. So looking at that, so let's put this. Here we added the 1. See the 1. Yeah. Then we add the second one to it. Program 2. 2. And then we have 1. So it's a 3, 3, 4, 5. Yeah. 1, 3, 4, 5. For numbers. And then what we did is we went here, this one, and it's this, not sure, then give us the right one, that's, no, it gave us the right one. 1006. The 46, they came from another, don't worry about the 46, but they gave us the, it's from the previous file. Yes, file. So this is mainly arrays in 2 ways. This is Endian. Remember, it's good to practice this. It's really important to understand the memory layout. It's really important. It helps a lot, guys. Helps a lot, especially in this. And next time we're going to do arrays of grouping as well. We're going to take one example just to demonstrate this more on how to rearrange an array. Let's say I'll have 2, 1, 3, two numbers and rearrange. And just to show you this. Okay, thank you guys, and see you next time.